Hi again, Dr. P here, and welcome to Lecture 2 for Chapter 1 in Chem 12A. Let me go ahead and share my screen and get started. All right. So in this lecture, we'll go ahead and take a look at how chemical bonds form. So what we're going to look at is valence bond theory, which is one way of describing the nature of chemical bonds. And one thing I do want to talk about is hybrid atomic orbitals. Because that's something that we will encounter pretty much over and over this semester. In addition, we should have time to talk about molecular orbital theory. If not, then I'll go ahead and put that in the next lecture. All right, so what is valence bond theory? Well, valence bond theory states that covalent bonds form when orbitals overlap with constructive interference. Now, what do I mean by constructive interference? Well, remember, an electron is a wave, or it has wave-like properties. So if we took two waves, and added them together, and they were in the same phase, that is, where the first wave was positive and the second wave is also positive, those guys are going to add constructively. We can contrast that to having waves of different phase, and when we add together our waves of opposite phases, they will cancel each other out, where the first one is positive, the second one is negative. So adding those together gets us basically nothing there. So we call that destructive. So again, our electrons behave like waves, so they have this property of interference when we try to add them together. And it is only when we have orbitals overlapping with constructive interference that we can get chemical bonds. Now, in particular, we can look at the energy of these bonds. So let's take a look at the energy of covalent bonds. I like to draw diagrams. That is something that you will see as this semester progresses. So let's put energy on our y-axis here, and we'll call this R, which is going to stand for our internuclear distance. That's going to be on our x-axis. So at some point, there's going to be a zero of energy here. Now, when our atoms, let's say we had a couple of hydrogen atoms here, are separate, we essentially are at zero energy. As we bring those atoms together, they will get lower in energy until they reach a point of minimum energy. And that is called the bond energy. And that distance where they're separate is called the bond length. So we've got HH, we've got this is our H2. These guys are covalently bonded together. So there's some minimum length that gives us our minimum energy. Now, it's not always the case that the hydrogens are just stuck next to each other like that. They can wiggle back and forth a little bit and might have a slightly shorter or slightly longer bond length and ever so slightly higher bond energy. We'll see how we can actually make use of that in identifying molecules later on this semester. Now, if we tried to smush these hydrogen atoms closer and closer together, we would see that the energy rises pretty rapidly until we basically have two hydrogen atoms on top of each other, which really we can't do. That just won't work. Okay, so this is a nice energy diagram that shows what's going on energy-wise when chemical bonds form. And the point here is that chemical bonds are favorable. They actually would release energy. Let's say they're exothermic or exergonic. They release energy when they form, which is a good thing for us, because if chemical bonds weren't favorable, then they wouldn't form and we wouldn't be here to be talking about this. So there you go. Good thing that chemical bonds can form. All right, let's take a look at some other ways that we look at our chemical bonds. And let's in particular pay attention to what's going on an individual molecule or in an individual molecule. Another part of valence bond theory is hybrid atomic orbitals. And an example would be, let's take a look at methane, CH4. Now we could draw it as a carbon in the middle, and we'll use sticks to represent chemical bonds. So each of these lines or sticks, each line is a covalent bond. It's a pair of shared electrons. Now, drawing it like this, it looks flat. Well, it's really not flat. Really, it's a three-dimensional structure. I happen to have a, well, actually it's ethane right here, but so this is what I'm talking about with 3 dimensions. It's not flat on the ground. It's got 3 dimensions here. And the wedge here indicates that that bond is coming out towards us. And the dashes indicate that the bond's going away from us. And the other bonds that are just lines are in the plane of the paper. So this is a standard way of representing 3D structures on a 2D piece of paper. And I'll talk more about this later, and you will want to get used to doing these types of drawings. So this structure, again, it's not flat, it's not planar, it is tetrahedral. And one question is, one question that we need to answer when we're trying to have our system of describing bonding. One question we need to answer is, how can methane be tetrahedral? Also, how can methane have identical CH bonds? So all of these carbon-hydrogen bonds are the same. Now, if we were going to try to describe what's going on here, we can draw I'm going to draw an energy diagram here. And so let's say we have carbon, and we use dots to represent electrons. So each dot is an electron. And of course, we've got our 1s electrons, our 2s electrons, and then our 2p electrons. And try to find a colored pen here. Here we go. So any electrons in the inner shells, we call those core electrons. In the outermost or valence shells, we call those valence electrons. So we have 6 total electrons in carbon. 2 are in the 1s orbital. Those are core electrons. The others are in the 2s and 2p orbitals. So if I was going to fill these up, I'd of course put 2 in the 2s orbital. So I've got 2, 4, I've got 2 more, and electrons spread out before they pair up. Remember that from Chem 1A. That's what, Hund's rule, I believe. Now, the way that I've drawn this, if we want to bring in some hydrogens, each hydrogen is going to bring 1 electron to the party. So we would want to, if we could, have our carbons there, and then we'll have hydrogens. Each hydrogen brings 1 electron to the party. And when we draw it like that, those pair of dots is 2 electrons. That is our bond. Okay, I prefer drawing the lines or the sticks to the 2 pairs of dots when I'm drawing electrons in bonds. If the electrons are just hanging out in what we call a lone pair, then I'll draw the dots. Now, the problem is, if I bring 4 hydrogens, each with 1 electron, yeah, when I draw them like this, you can see how they pair up. But when I draw the electron energy diagrams of the hydrogen, I've got a 1s electron in each hydrogen. That's a valence electron. Okay, I can pair up here, I can pair up there, but now I've got an empty orbital. I can't pair up in that. And I'm not allowed, I can't bring 2 hydrogens, each with an electron, and try to get them to pair up in 1 orbital. That would be 2 hydrogens bonding to 1 orbital, which is just crazy talk. So what we need to do is we need to hybridize. So hybrid atomic orbitals are mathematical reconstructions of atomic or regular atomic orbitals. They're blends or averages of atomic orbitals. So we'll say mathematical averages of atomic orbitals. The key thing is here, they also satisfy the Schrodinger equation. That's what all these orbitals and quantum mechanics stuff is about, satisfying the Schrodinger equations that we can describe our atoms here. So we can do this mathematically, and it gives us a picture that's more accurate. So that's what we do. Again, these are models for what's really going on, and they happen to be pretty accurate. We'll see cases where valence bond theory works better and where molecular orbital theory works better as well. Anyway, our 1s orbital stays the same here, but now instead of 2s, we will have sp3 orbitals, sp and then a superscript 3, sp3. Each of those will have 1 electron. So the sp3 orbitals are averages of the s orbital and then all 3 p orbitals. So we're going to end up with 4 orbitals. We started with 1, 2, 3, 4, so we get 4. They're all the same, they're all equal in energy. And now we can bring in the hydrogen electrons here in blue and pair those up. And now we've got all of our CH bonds are identical. And when you actually look at the math of the sp3 orbital, they end up being tetrahedral as well. So hybrid atomic orbitals will explain the structure or the shape, geometry of atoms, and also how many bonds that atoms will tend to form. Now, another way to view this is to, and this is Dr. P's bad artwork here. We can have carbon, and these bonds tend to be kind of these, or rather these orbitals tend to be these lobe things. Lobe is not really a word, but they're kind of these, sort of blobby lobes. And where I've drawn colored in black here, we have overlap between the s orbital, which is the sphere here, a little ball around the hydrogen, and the sp3 orbital on the carbon. And so when we get overlap like that, we call that a sigma bond. And this is what methane looks like. We can do ethane, so C2H6, ethane, where we'd have C, and then we'll put our H's in here. And then we also have another sigma bond, and that is the Greek letter sigma there. And in this case, the sigma bond is overlap between sp3 and sp3 orbitals of our 2 carbon atoms. So a sigma bond is orbital overlap between nuclei and along the internuclear axis. And here is my model to show this. Okay, these gray things are our orbital overlap, and not all the orbitals are, well, I guess they are all shown actually, but they're not shown individually, it's just shown as the overlapping part. So here's our sp3, sp3, sp3. Here's our sp3, sp3 overlap. And so this is ethane. This is what ethane looks like. Okay. Now, what if we have things that are maybe a little different? What if we had ethylene? C2H4. Now, the way that we typically draw this is like so. Where the two lines in the middle indicate a double bond. Now, in this case, we are going to have three things attached to each carbon. And when we have three things attached, we're going to get sp2 hybridization. I will post a guide to drawing Lewis structures, which we'll talk about in a couple of lectures. And so you can review that, brush up a little bit on drawing things like double bonds, etc. This is also trigonal planar. The bond angle of 120 degrees. And that's the angle between those bonds. So let me draw this here. And I'm just going to draw the valence electrons. And when we hybridize, we will get one electron in each of the, these are sp2, I'm sorry, these are sp2 orbitals. So I've taken the s orbital and then two of the p orbitals, recombined them to make three equal sp2 orbitals. There's one p orbital left over. Now, why is there an electron in there, not in there? Well, in this case, the energy gap here is small enough that we can get an electron in a p orbital. It's actually lower in energy than pairing up with another electron. So what we end up getting then is we'll get our let me try to draw this here. We'll get our sigma system. So we can see here that we've got a sigma bond. Sigma bond there. But then we also have our leftover p orbital. And this really isn't drawn to scale, but our leftover p orbital we can have overlap. And we call this a pi bond. Our electron density is in between the orbitals, but not on the internuclear axis. And then, of course, these guys here are, that's an sp2 orbital, sp2, sp2, sp2. So what this ends up looking like then is this, actually. So let me just cover this up. Here is my p orbital. And the two lobes are different phases. So that's why they're colored different colors. So, instead of saying positive or negative, it's just pink and purple. So when they line up like that, that's good constructive interference. And now we get a bond. So we have overlap with the p orbital. Both lobes of the p orbitals will overlap. So pink lobe of one with pink lobe of the other, purple lobe of one with the purple lobe of the other. That makes one pi bond, okay? These two things together, those two regions of overlap together, is one pi bond. And now our double bond is going to be one sigma bond plus one pi bond. Now we can have even more, even a higher bond order. We can make a triple bond. So let me draw that for you guys. An example of that is acetylene. And here we've got our bond angle is 180 degrees, making our molecule linear. And in this case, we're going to take our 2s, our 2p orbitals. We will hybridize. And we will get now, boom, 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 sp orbitals, and then we'll have leftover p orbitals, and we'll have one electron in each of those. So now what things end up looking like is we've got our linear carbons here. The carbons are in a line. Hydrogens on the ends. This is what we would call a sigma system. And then we actually have two sets of pi bonds. So I'll draw one like this. So we've got p orbital, p orbital. And then this is all flat in the plane here. Then coming out and going behind the plane of the paper, we have another pi bond. Which is perpendicular to the first pi bond. And so these two pi bonds combined with the sigma bond make the triple bond. And then this is the result. Okay, so we've got one pi bond here, purple and pink, and that's in sort of the plane here, and then coming out and going behind is the other one. And so this is our triple bond. Now, we can get some interesting things And one of them is benzene, which is C6H6. And benzene is interesting because if we were to draw the Lewis structure, it would look like this, alternating single and double bonds, but that's not really accurate. Actually, all of the CC bonds in benzene are the same length. And so we can draw a resonance structure. I'll talk more about resonance structures later. And sometimes we would just represent this as this hexagon with a circle in it. Resonance structures are equally valid Lewis structures. And it's not that half the time the molecule is one and half the time it's the other. It's that all the time the molecule is an average of these two. Now, what this ends up looking like is we're going to have our carbons with a sigma system, and then all of these p orbitals. So one p orbital for each carbon. And then we have now a pi system. Oops, pi system. And so it looks something like this. Now all of our p orbitals all overlap with each other. So those pi electrons are now spread out over the whole ring. So we don't have just that guy or just that guy. It's really a blend of the two, which sometimes we draw like that because this representation shows us that, oh yeah, things are spread out over the whole atom. Now, if another way of analogy to talk about it is your ethylene is kind of like a hot dog. The sigma bond is the hot dog, and then the bun is the pi bond. Acetylene is a bagel dog. You've got your sigma bond is in the middle there, and then the dough of the bagel dog all around is the pi bonds. If that's the case, then I guess a benzene would be kind of like a hamburger, where the bun is the pi bonds, and then the meat is the sigma system. So it turns out that sigma bonds are great for describing some things, or maybe I should say valence bond theory is great for describing sigma systems. But when we involve pi systems, sometimes we have to make things a little bit more complicated in order to describe things a little more accurately. So in the next lecture video, I'll go ahead and talk about molecular orbital theory, which is where we get into something a little more complex, but hopefully a little more useful for some things. All right, so until next time, stay safe out there.